In this question, we've got an RC circuit. Initially, the switch is open, so no current is flowing, and the capacitor is uncharged. We close the switch at t equals 0, so we'd like to analyze this circuit and find an expression for the charge as a function of time. In class, we did current as a function of time, or we did the discharging circuit. So the charging circuit is not that different. We'll go through the same process. So what happens is at t equals 0, we close the switch. So that happens at t equals 0. As soon as the switch is closed, charge starts to flow. If charge is flowing, we have a current in the circuit. So we get a current flowing around the circuit at some random time t. So this is after the switch is closed, but before everything is fully charged. Let's say that the current in the circuit, we'll call that I. So this current is flowing around the circuit, and the charge on the capacitor is Q. So there's some things we have. Let's write Kirchhoff's potential law going around the loop this way. So our potential law states that we have a potential supply by the battery, which we'll call epsilon, so that's our potential or our voltage of the battery, minus the drop across the resistor from Ohm's law, V equals IR, so that's I times R, and subtract the amount of potential that goes onto the capacitor as we get it charged up. Remember, for a capacitor, capacitance is charge over potential, so then potential is charge over capacitance. So there's our potential law. This is going to give us the information we need to find an expression for our current. The next part we need to substitute in is how is current related to charge? Well, current flows around this switch, so we know that current is charge over time. I is dq over dt. I can either be, the dq over dt can be positive or negative. Let's remember that what happens in this circuit, when we close the switch, the charge starts to flow. The charge on the capacitor starts to increase when the current flows in this orientation. So that means that our current would be plus dq over dt. We get the current flow when the charge on the capacitor increases. That's different from the discharging capacitor. So now we have a solvable problem. What we have to do is put our dq over dt in here, and then we'll solve that expression for q. So now we just move on to a calculus problem. So epsilon minus dq over dt times r minus q over c equals 0. First thing let's do with this problem is let's get the c out of the denominator. So we'll multiply through on both sides by c. That gives us epsilon times c minus dq over dt times rc minus q equals 0. Let's get our q terms on one side, or let's get our dq over dt on one side. So epsilon times c minus q equals dq over dt times rc. And what will we do next? Let's bring our d. So then let's get the q term over here on this side and get the other stuff on the other side. So 1 over rc equals 1 over epsilon c minus q dq over dt. Okay, now we're doing pretty well. Let's get our dt up to this side. 1 over rc times dt equals 1 over epsilon c minus q dq. So now to find our expression for charge, let's integrate both sides. So the integral of 1 over RC times dt equals the integral of 1 over epsilon c minus q dq. We need to integrate over the limits of our problem. On this side of the integral, the limit of time is it goes from 0 to some time t, because we're trying to find an expression for the charge as a function of time. For our charge size, it goes from 0 to some charge q. So q is the amount of charge it would have at time t. So this integral is really easy. Take our 1 over RC outside. The integral of dt is t. That's going to be evaluated at t and 0. On this side, the integral of 1 over epsilon c minus q gives us minus the natural log epsilon c minus q. That guy is going to be evaluated at q and 0. So for this one, we get 1 over RC times t minus 0 equals minus natural log of epsilon c minus q, subtract minus natural log epsilon c minus q. Oh, minus 0. There we go. Didn't want to drop that 0. So we have t over RC equals minus natural log epsilon c minus q minus natural log of epsilon c. We can use our logarithm identity that if you have the log a minus log b, that's the log of a minus b. So now we're trying to solve for our charge q. Let's get our minus over to the other side. So minus t over RC equals natural log epsilon c minus q over epsilon c. To get rid of our natural log term, we raise both sides to the power of e. E to the minus t over RC equals epsilon c minus q divided by epsilon c. Now we want to solve for q, so this is equal to 1 minus q over epsilon c. So q over epsilon c equals 1 minus e to the minus t over RC. So we'll multiply both sides by epsilon c. Q equals epsilon c 1 minus e to the minus t over RC. Okay, now let's have a look at what we have and see, are we close to our final answer. Potential times capacitance, that's charge. Okay, and we would get the maximum charge when we had the maximum potential. So this is maximum charge, which we can call Q maximum, or keeping with the notation from class, we can call that Q0. It doesn't really matter what you call it. And then also in this part, R times C, that's what we've defined as tau, our time constant. So then Q equals the maximum charge, 1 minus e to the minus t over tau. And there's the expression we were asked to show. We'll go on and we'll use this expression in the next parts of this problem.